Good morning, student. Today we are going to learn about phase shift keying. After the completion of today's session, you are able to define phase shift keying, explain the generation and detection process of phase shift keying. Phase shift keying can be represented as PSK. Okay, so a digital modulation technique that transmit data by changing the phase of the carrier wave in accordance with the digital modulating signal is called PSK. The easiest form of PSK is BPSK, that is binary phase shift keying. So today we will discuss about this BPSK. Okay. Here each signaling element is represented by a single data bit. Means each symbol represented by a single data bit. Here the carrier undergoes two phase reversal such as 0 degree and 180 degree. Means here at a time we transmit a single bit 1 or 0. As here two levels are present, so the phase reversal occur in 0 degree or in 180 degree, means in two levels. Okay, let us assume that the carrier is given as C of t. As we know, C of t equal to A cos omega ct, means omega c means 2 pi fc. So A equal to amplitude of the carrier signal and the power dissipation is P equal to A square by 2, and from this equation we can derive the value of A, that is A root 2p. So we just substitute this value here, otherwise it is A cos omega ct, same. Next, when 1 is transmitted, at that time the BPSK signal is represented as root 2p cos 2 pi fct. So here we can say 1 is multiplied, means plus 1. Like this, when symbol 0 is transmitted, the BPSK signal is minus root 2p cos 2 pi fct. The only difference is plus and minus. When we combinedly represent these two equations, then the BPSK signal is B of t root 2p cos 2 pi fct, means B of t is plus 1 when binary 1 is to be transmitted and minus 1 when binary 0 is to be transmitted. So this is the waveform. Here one thing, here why for symbol 0 a negative sign is coming here? Because here phase is changing, 180 degree phase change occurs here. Because of that, in the equation of carrier signal, cos omega ct plus pi we add. Pi means 180 degree. So as we know the mathematical formula, that cos theta plus pi equal to minus cos theta. So for that, here we get minus root 2p cos 2 pi fct. Okay. So next let's see this diagram. So in this diagram, first one is the bit stream, but here the bit stream is unipolar. Why unipolar? If this black line is the center line, means above the black line is the positive region and below the black line is the negative region. Here you can observe that the signal is only present in the positive part, means polarity is a single polarity, so this signal is known as unipolar. But for BPSK we have to convert this unipolar signal into bipolar, means in the second diagram you can see the signal is present in upper half and lower half. So in positive half and negative half, in both the half the signal is present, means the signal becomes bipolar signal. Then the third one is the carrier signal. Then last one is the BPSK signal. So the figure shows phase reversal when the bit sequence gets changed either from 1 to 0 or from 0 to 1. Okay, this line means from 1 to 0 and this line from 0 to 1. When the bit sequence changes from 0 to 1, then we noticed a positive phase change. Okay, 0 to 1 means here you can see this line is 0 to 1 conversion. Here you can observe that the phase change is positive. Then whereas when the bit sequence changes from 1 to 0 means this line, okay, 1 to 0, then a negative change of phase is noticed here. The negative changes occur. Okay. Next is the generation of PSK, or we can say BPSK, because now we are discussing about the easiest form of PSK, that is binary phase shift keying. The block diagram is consist of a bipolar NRZ level encoder, balanced modulator and carrier generator. As we discussed before that we have to convert the unipolar signal to a bipolar signal. So for that here we use a encoder. Encoder convert the incoming digital signal which is in the form of unipolar, it converts it to bipolar signal. Then in a balance modulator we have to give two inputs. One is the output of this encoder and another input is given from the carrier generator, or we can say local oscillator also. So it gives the carrier signal to the balance modulator. Then the balance modulator at the output gives the modulated signal. So we can say BPSK signal. Next is the detection of PSK signal. This diagram is consist of square device, band pass filter, frequency divider, synchronous demodulator. This is also known as multiplier. Okay. Then bit synchronizer, integrator, decision device. So first we receive the signal that is transmitted from the transmitter section. So this signal is received by the receiver section, but in the transmitter section we transmit only this much signal, there is no theta present. So why here theta is showing? So the signal undergoes the phase change depending upon the time delay from transmitter end to receiver end. We always know that when we are transmitting something there must be a time delay present due to the distance. So because of that a phase change occurs which is represented here with theta. Okay. Then this received signal is given to the square law device. Okay. This one is the first block. So we apply this phase changed input signal, received signal to the input of the square law device. Then at the output of the square law device we get this signal. Okay. So here only the carrier of the signal is taken into consideration because the amplitude is neglected. So mathematical formula you know that cos square theta, that is 1 plus cos 2 theta by 2. This formula is used here to solve the cos square 2 pi fct plus theta. So using this formula we write here 1 plus cos 2 bracket start 2 pi fct plus theta bracket close whole divided by 2. When we simplify this, that is 1 by 2 plus 1 by 2 cos 2 into 2 pi fct plus theta. Then this signal is given to the input of the band pass filter. Okay. So in this signal, this 1 by 2 is the constant value. So we can say this is a DC level. So this signal pass through the band pass filter, and band pass filter removes the DC level, that is 1 by 2, and at the output we get, after removal of this 1 by 2, only this much we get at the output. So see, cos 2 into 2 pi fct plus theta at the output of the band pass filter we get. Then the output of the band pass filter given to the frequency divider. Here the frequency divider is divided by 2. Okay, so the signal, we divide the signal by 2, so 2 cancelled out. So at the output of the frequency divider we only get cos 2 pi fct plus theta. Okay, this one is the output of the frequency divider. Then the output of the frequency divider given to the synchronous demodulator or multiplier. To the synchronous demodulator we have to give another input here. So that is the received signal by the receiver is given here. So the synchronous demodulator is a multiplier, so it simply multiply these two signal. See here, this one is the received signal by the receiver and this one is the output of the frequency divider. It simply multiply these two signal. So at the output of the multiplier we get b of t root 2p cos square 2 pi fct plus theta. Then we apply the formula, that is cos square theta equal to 1 plus cos 2 theta whole divided by 2. So same formula is applied here. Then we solve this and get the final equation, that is b of t root p by 2 1 plus cos 2 into 2 pi fct plus theta. So then the output of the multiplier given to the integrator. So here a beat synchronizer is used, and this beat synchronizer control these two switches, that is S1 and S2. Okay, so the output of the multiplier is then applied to the beat synchronizer and integrator. The integrator integrates the signal over 1 beat period. Okay, so the beat synchronizer takes care of starting and ending time of a beat. Okay, this is the work of this beat synchronizer. It takes care of the starting and ending of the beat. At the end of the beat duration, the beat synchronizer closes switch S2. Means when we give the signal to the integrator for 1 beat period, it closes S1, and integrator integrates the signal for only 1 beat period. After the completion of 1 beat, it opens the S1, then close this one. So the output of this integrator given to the decision device, which decides whether transmitted symbol was 0 or 1. The synchronizer then opens switch S2 and again close the switch S1 temporarily. Means the process is repeats again and again. Means it closes for 1 bit period, switch S1, then after the end of the bit it opens it and close the S2, then for short period of time it close the S2. After the signal applied to the decision device, it again opens the switch S2 and close the S1. Means this process is repetitive process and the process is continuous again and again. So this is all about BPSK. Thank you.